So we have seen how to implement the convolution layer programmatically. Now how do you implement the fully connected layer? This should be very simple. Once you get the feature map output, you stretch it to a one-dimensional vector and just take the dot product with another filter to give you some scalar output. So what is actually happening in a dot product? You are doing the element-wise multiplication, okay, of all these values. Whatever products you are getting, you are just adding up all the values to get a single scalar output. So that is what is happening in a dot product. If you think about it, if you go back to this example, here what is happening in this case, in the fourth case, we are taking the element-wise multiplication of all the elements in the matrix. That is, you are multiplying 9 with 1, 7 with 3, 8 with 6 and so on. Whatever values you are getting, you are just adding it up to get a single scalar. So if you think about it, even the fully connected layer can be implemented as a convolution operation. That is, you take the same filter and represent it as a matrix. And this matrix should have the same size as that of your feature map. Here my feature map is of size 4 by 3. So even my matrix, you have to represent it as a size 4 by 3. Which should make sense because here we have already learned that this feature vector, if it is of size 12, even your filter should be of the same size as that of your feature vector. So the same constraint can be carried forward even in this case. If you are doing the convolution, the matrix size, that your filter size should match the feature map size. And then you just apply the convolution operation. So here also you are just doing the element wise multiplication of all the values in these two matrices. And finally, once you multiply, you are just adding up the products. So if you try this out, if you try the convolution operation out, again you will get the same score that you got in the dot product of these two vectors. So finally, the conclusion is that even your fully connected operation can be implemented as a convolution. This is not a rule, but I'm just giving you what are different choices you have. So in this example, what is happening here, once you finish the pooling layer operation, you are getting these two matrix outputs. You expanded it into a one-dimensional vector and did the dot product with these two filters to get some values, and then you did the softmax. So instead, what you can do is you can append these two matrices like shown here, and then this filter you can represent it as a matrix, and even this, and then you just do the convolution with these feature map. These will be the values that you will get. Okay, so this is another way of doing the fully connected layer operations as a convolution operation itself. Now you might wonder, why am I spending so much time explaining this? Because it's useful in one of the papers. We'll see that in some papers the fully connected layer operations is done as a convolution operation itself. So I just wanted to give you this concept beforehand. Finally, I never explained to you how we are getting these weights here, both in the convolution layer and also in the fully connected layer. In the examples that I have given, I have manually come up with these values in the weights. And if you are doing the classical computer vision based technique like hog and sift, you are doing the math, you know the math behind it, and you come up with these SVM coefficients, and these weights you use for classification. But in the case of convolution neural network, I don't use any of these techniques. So how do I get these weights? So that's the question that I never answered until now. We'll see more details about it in the next video. I'll only try to give you the intuition, but I'll not be going into the details.